We're going to do a gravity experiment to teach you a little bit about the relationship of velocity and the acceleration of gravity. And the questions we're going to consider in the experiment are: if an object falls through a distance h, how fast is that object going at the bottom of its fall? What we're going to use in this case is a ramp, not just a direct fall. Galileo in the early 1500s did the experiment, supposedly dropped a couple of balls from the Tower of Pisa, a heavy one and a light one, and showed that the heavy one fell at the same rate as the light one, counter to the expectation of the people at the time. So how fast is the object going at the bottom of its fall? We're going to have some steel balls, big one that's heavy and a small ones that are less heavy. So we're going to compare those rates of fall. If an object slides down a ramp or rolls down a ramp of height h and length l, how fast is it going at the bottom? Well, we have a ramp, and then we have measured off the L, and we're going to measure the H. And so we'll make that experiment too. Does the speed at the bottom depend on the slope of the ramp? We're going to try a couple of different slopes and see if it depends on that or just on the height, initial height. Does the speed at the bottom depend on the mass of the object? Okay, that is answered by the 3 steel balls, and that's suggested by Galileo's Leaning Tower of Pisa experiment. So the theory is over here. I don't really expect you to be able to solve equations yet, really, but they're not any more complicated than you'd think they'd be. Equals simply means is the same as. So the theory here is that the potential energy, the energy that's stored up by lifting the ball to the top of the ramp, is the same energy as the moving energy or kinetic energy the ball has at the bottom of the ramp. And if you want to figure this out, and physics is all about figuring things out, the mass of the ball times this gravitational constant, 980 centimeters per second squared, 980 centimeters per second squared, that's an acceleration of gravity, times the height change in centimeters, which we're going to measure, is equal to 1/2 of the mass of the ball times the speed of the ball at the bottom of the ramp squared. So in equation form, that's m, the mass of the ball, times g, the acceleration of gravity, times h, which is the height difference the ball falls through, is equal to 1/2 mv squared, where v is the speed of the ball at the bottom of the ramp. Now, if you do the algebra, which you also haven't gotten yet, solve that equation, you can find out what that v is in terms of the other variables in the equation, and it's just equal to the square root of 2 times g times h. 2 times 980 centimeters per second squared times h. Now, h is the difference between the height at the top of the ramp and the height at where the clock turns off at the bottom of the ramp, and I'll show you the apparatus in a minute. So, one thing about this equation is the speed doesn't depend on the mass or the weight of the ball, only the height change. And it doesn't depend on the slope of the ramp or whether it's a flat ramp like ours. Think of a roller coaster, for example. If the roller coaster falls through height h, you can tell what its speed is at the bottom without knowing what the mass of the roller coaster is or the form of the curve it goes through to get to the bottom. Okay, so now the questions we'll answer today, and you'll do the experiment. Do light objects fall slower than heavy ones? Actually, we may find out that the lightest object does fall a little slower than the heavy one, but we might have some explanations for that don't discount the question of conservation of energy. Does the speed of the ball depend on the height change as determined in the graph? And this is a graph of the equation that we saw over here, mgh equals 1, it's the v equals square root of 2 times g times h. So if you plot that on the graph, it looks like that. Now if our data points fall pretty close to that line, it means that our theory was correct, or at least it's predicted the data. Okay, now doing the experiment, what we're going to do is we'll set up the ramp, and it's pretty much set up. Measure the initial height and the height of the clock stop sensor. The initial height is the height from which we drop the ball, and the clock stop sensor is where the timer turns off. So it's the time it takes to fall from the initial height to the clock stop sensor. So that's what h is. We're going to measure the distance the ball will roll while it's being timed. That's along the ramp. And we're going to push the button to hold the ball to the starting point. Then we're going to release the ball and catch it at the bottom. And the time will show up on a timer, which I'll show you in a minute. And then we're going to repeat that measurement, each measurement 5 times. And we're going to change that ramp's angle and the height from which the ball falls, which of course will also change when we change that angle. So we're going to do a whole bunch of data points. We're going to write them down on a data sheet, and then we're going to analyze the data and find out if those data points all fall along that line. And we're going to find out whether we think the speed depends on the mass of the ball. So we have three balls. We're going to measure the diameter of the balls and write that down because I don't have a way of measuring the mass of the ball. So we're going to measure the diameter, and I'm going to calculate the mass for you using the density of steel, which is about 8 grams per cubic centimeter. So here we're going to measure the diameter of the ball, and I have a centimeter stick here, and we're going to put the ball on the end of the stick, and I'm going to eyeball it. It looks like this ball is 2 centimeters in diameter. Looks like this ball is 1.5 centimeter in diameter, and the small ball is 1 centimeter in diameter. Okay. So the big one is 2 centimeters. It's 2 centimeters diameter. The middle one is 1 centimeter, 1.5 centimeters. And the small is 1 centimeter. Okay, now I'm going to show you the experimental apparatus, and that's this. And we'll try to back out a little bit so you can see a little more of it. This is the slope. The top, there's an apparatus for releasing the ball, and there's a circuit at the bottom. And what we're going to do is we're going to hook this circuit up to a power supply, which is this big battery down here. And see, the timer lights up. There's a button on that circuit, which I'm going to push with my thumb. It clears that counter. You can see it's all zeros now. But if I release that button, the timer starts running. And it's counting seconds. 3, 4 point, and then those 2. So this is seconds. And these two are tenths and hundredths of a second. But when the ball crosses this line here, it stops the timer. So if I take the middle ball and I push this button, let me put these balls back over here. If I hold this down and that holds the ball at the top. We'll look at this distance from the bottom sensor to where the ball is, and it's 43 centimeters. Now if I release this, the timer starts running, but it's going to stop when it gets to this point down here, 0 point. So we got 0.42 seconds. So what we would do is write down this diameter of the ball. It's the intermediate ball, 0.5 centimeters diameter, and the initial height, which we haven't measured yet, which I'm going to do right now. And so the initial height was up here. Looks like it's right at 30. It's about 30 centimeters. And the bottom sensor is right down here. And it's right at 5 centimeters. So it's 30 centimeters minus 5 centimeters, or 25 centimeters initial height. So I'm going to write that down on the sheet. This is something you need to do also. See the sheet. Now, the height of the initial was 30. Height of the clock stop was 5, so the height change is 25. And the distance from the top of the ball to the clock stop is on the ramp, and it's 0 at the bottom sensor of the clock stop, and at the top the ball has a diameter, so it starts out here. So we're going to say that it's this number here, which is 4123.5. So it's 43.5 centimeters. So let's say the distance is 43.5 centimeters. And the time, we read off this timer here, is, I'm just going to stop it, clear it out, we'll do it again. It's 0.42, that's 0.42 seconds. So it's 0.42. Now the average velocity we can calculate as being the distance it traveled, which is 43.5 centimeters, divided by the time, which is 0.42. So it's averaging about 100 centimeters a second, or 1 meter per second, going down the slope. We're going to calculate all that stuff at the end, because it's easier to do it with a spreadsheet than it is to actually do it in your head or even use a calculator. But okay, so let me now turn off this camera and reset it up so that you can see the whole thing, and we're going to do the experiments. When we do these experiments, we're going to repeat them 3 times for each set of conditions. Then I'm going to change the slope. I'm going to repeat the experiment, but I want to get the magnification out so you can see the whole picture. So we're going to